morning, dear students. Welcome back to my class. Electrochemistry part 2, that is the galvanic cell. So last class we have been discussing about the electrode single electrode potential and different classification or different types of single electrode potential. And today we are going to detail the 4 different types of single electrode and the electrode reaction involved and the Nernst equation for the corresponding electrode reaction. And thereby I wish to introduce before you the reference electrodes. Okay. So different types of single electrode. Last class I mentioned that there are mainly 4 different types of single electrode. That is, they are classical metal ion electrode, 2 the gas electrode, 3 metal insoluble metal salt and soluble salt solution containing the anion of the salt, insoluble salt, and 4 is the typical oxidation reduction or redox single electrode potential, single electrode, like ferrospheric combination which a platinum electrode is dipped, or a stannous in which a platinum wire is dipped. Okay, are the typical redox single electrode. So first we have to discuss the metal ion. The classical example of the single electrode are our conventional metal ion electrode. Metal ion electrode. This is the conventional classical example of a single electrode. Any metal M solid is in contact with its salt solution. Okay, like N plus aqua in contact with the M. Okay, that is. And the electrode reaction involved are, that I have mentioned, the single electrode reaction is customarily expressed in terms of the reduction according to IUPAC system. So according to IUPAC convention, any electrode reaction should be represented in terms of reduction, that is addition of electron, so that the metal ion plus N plus aqua reversibly gives, plus N electron reversibly gives M solid. So this is the electrode reaction involved in the metal ion electrode. The electrode reaction. The electrode reaction involved in the metal ion electrode is N plus aqua plus N electron reversibly give M solid. That is, a conventional metal ion electrode is an electrode reversible with respect to the metal ion. Okay, so that the single electrode potential according to Nernst equation is given by E N plus aqua or M is equal to E0 Mn plus aqua M minus 0.0591 by N log M solid, that is 1, M solid 1, M solid, that is actually 1 divided by Mn plus aqua. Oh, that is equal to E0 single electrode plus 0.0591 by N log Mn plus aqua. So this is the final equation for the single electrode potential of a conventional metal ion electrode. So any such class of metal ion electrode comes under this category, like copper 2 plus, zinc 2 plus, then cadmium 2 plus, all comes under this category. So you can represent like this, that is example are Cu 2 plus, okay, I can represent it. That is single electrode like this, Cu 2 plus bar Cu, then Zn 2 plus bar Zn, Cd 2 plus bar Cd, Ag plus bar Ag. Okay, all this example comes under this category. Okay, and the magnitude of the single electrode potential and their sign I will explain to you later. Okay, the value of the single electrode potential is either negative or positive depending on its position with respect to the reference hydrogen electrode. Okay, with reference to hydrogen electrode. Okay, that I will explain the things later. The sign of the single electrode potential I will explain later. That is this first case. Then the second case is, the second case of single electrode are the gas electrode. The gas electrode. Example are hydrogen gas electrode, oxygen gas electrode, and chlorine gas electrode, etc. Okay, these are the example of gas electrode. Typical example of an is usually employed hydrogen gas electrode. It consists of an hydrogen gas, perfectly pure dry hydrogen gas at 1 atmospheric pressure or 1 bar is passed through a aqueous solution of hydrochloric acid or H plus ion concentration. Is in contact with H plus ion concentration, HCl solution of desired concentration, okay, particular concentration C, and in which platinum is in contact. Platinum foil or platinum strip is connected platinum wire is acting as an electrical contact. So it can be represented like this: platinum, comma, hydrogen gas at 1 bar, okay, 1 atmospheric pressure, or it is in contact with the H plus ion, HCl, aqueous solution of concentration C. So this is a typical example of hydrogen gas electrode. So if that it consists of a vessel containing hydrochloric acid, HCl, okay, containing H plus ion of desired concentration, in which a cell is inverted in this manner. A cell in which a platinum wire connected to a platinum foil, a strip is introduced, and hydrogen gas is admitted, H2 gas, at 1 atmospheric pressure. 1 bar or 1 atmospheric pressure is admitted so that the hydrogen gas bubbled through the solution. This is a typical example of that is assembly of hydrogen gas electrode. So hydrogen gas at 1 bar or 1 atmospheric pressure is bubbled through a solution of hydrochloric acid or particular concentration C, into which a platinum foil connected to a platinum wire for electrical contact. So depending on the concentration of H plus ion, this gas electrode, hydrogen gas electrode, develop a potential. Then if the concentration of hydrochloric acid is exactly 1 molar, if HCl or H plus ion is a concentration 1 molar, okay, 1 molar, and the hydrogen gas is excited at 1 bar or 1 atmospheric pressure, and T is at 298 Kelvin, then the potential developed in between the hydrogen and H plus ion is arbitrarily fixed as 0, then E0 is taken as H plus bar H2 is taken as 0, and that is called a standard hydrogen electrode. So what is a standard hydrogen electrode? A standard hydrogen electrode is a gas electrode in which a perfectly pure dry hydrogen gas at a 1 atmosphere pressure is bubbled through an aqueous HCl solution of concentration 1 molar, exactly 1 molar, okay, and kept at a temperature 298 Kelvin. Its potential is, single electrode potential is arbitrarily fixed as 0. Then it is considered as a primary reference electrode. It is the only primary reference electrode. Okay, any other electrode is standardized with respect to this primary reference electrode. Okay, so only one primary reference electrode is SHE, and its potential is taken as 0. And it is an electrode that is reversible with respect to H plus ion. That is another thing you have to remember. It is an electrode, hydrogen gas electrode, is reversible. It's an electrode reversible with respect to H plus ion. H plus ion. The reaction involved is, okay, 2H plus aqua plus 2 electron reversibly gives H2 gas. So this is an electrode reaction in terms of the reduction. So in terms of reduction, the electrode reaction is represented like this: 2H plus aqua plus 2 electron give H2 gas. So the electrode reaction in terms of reduction involved in a hydrogen gas electrode is this. So it is called an electrode in which hydrogen gas is reversible with respect to H plus ion. So it can be again written as, that is, H plus aqua plus electron reversibly gives half H2 gas. Both are correct. Okay. So when it is called SHE, okay, I explained. And what is potential, that I also explained. The Nernst equation is E. If it is other than 0, okay, if it is the concentration is other than 1 molar, then H plus bar H2 platinum is equal to E0 H plus or H2 platinum minus 0.0591 by N1, okay, or N2, whatever may be the case. If you are taking this equation as 1 log half H2 by H plus, half H2 is 1, take it as 1 by H plus aqua. So this is the electrode reaction involved and can be taken as, this is 0 plus 0.0591 log H plus aqua. So the electrode reaction involved in a hydrogen gas electrode is like. So depending on the concentration of H plus ion concentration, depending on the concentration H plus ion, or depending on the pH, okay, depending on the pH of the solution, or depending on the concentration of H plus ion present in the acid solution, it develops a potential. I think as electrode develops a single electrode potential, and the single electrode potential of standard hydrogen electrode is 0, because for 1 molar solution HCl at 1 atmosphere pressure, hydrogen gas bubbled through at 1 atmosphere pressure at 290 Kelvin, its potential is 0, so SH is 0, so it is like this. So it is equal to 0.0591 log H plus aqua. When this becomes 1 molar, it will automatically become 0. So that is the thing. So hydrogen gas electrode is a single electrode, gas electrode reversible, in which hydrogen gas is reversible with respect to H plus ion. The next thing, the third electrode, reversible single electrode, third class or third type, that is metal insoluble metal salt in contact with the soluble salt of the metal ion of next same anion of the insoluble salt, like that is Hg metal, insoluble metal salt of the metal Hg2Cl2, that is solid insoluble salt, that is calomel, which is in contact with the aqueous KCl. KCl, that is Cl minus, aqueous solution. Okay, this is an example of a metal insoluble metal salt, soluble salt of the same anion of the salt. Then Ag, AgCl solid contact with Cl minus aqua. This KCl or Cl, I guess. Okay, this is an example of metal insoluble metal salt. Here, the electrode is reversible with respect to the anion of the salt, like this. That is, this is the first category. The mercurous chloride in contact with the chloride ion is called a calomel electrode. The first category is called a calomel electrode. And this is called a standard silver electrode, silver chloride electrode. This is calomel electrode, and depending on the concentration of the KCl, whether it is 0.1 or 1 molar or saturated, it has a known potential, and it is a secondary reference electrode. Okay. So this is usually called a calomel electrode, and the assembly of the calomel electrode I have mentioned. I can see you calomel electrode. It's an assembly of calomel electrode. You look at the picture. So look here. Okay. This is a glass tube with a side tube and a side bent tube. And the glass tube, the bottom portion of the glass tube is filled with some mercury. Okay, first it consists of mercury liquid, and above which there is a paste of mercurous chloride or calomel is pasted, and above which there is a saturated solution of KCl. The KCl solution is introduced through the side arm of the tube. Then it is closed, and it is then connected to a platinum wire, a glass tube containing platinum wire, which is sealed to some mercury, and it is inserted into the mercury at the bottom. So the platinum acting as the electrical conductor, and the bent side tube, a U-type, which is acting as salt bridge for any coupling or connection. Okay, joined with any other electrode. It contains aqueous KCl solution. This KCl solution is also taken in this bent tube. So this is the pictorial the schematic representation of a calomel electrode. A glass tube, its bottom portion is containing little mercury, above which is some mercurous chloride, and above which KCl solution, saturated KCl solution usually, and KCl solution is introduced into the side tube. Then it is closed with a cork containing, to which a platinum wire sealed through a glass tube, and little more mercury is inserted to the bottom portion, which acting as the electrical conduct. A U-tube, side bent U-tube containing KCl is also attached to it. So the electrode reaction involved in this, that is, in terms of reduction, Hg2Cl2 solid plus 2 electron reversibly gives 2Hg liquid. 2Hg liquid plus 2 Cl minus aqua. So the electrode reaction involved in this is, so it is an electrode in which the mercurous chloride or insoluble metal salt is reversible with the chloride ion. Or mercurous chloride, a calomel electrode is that electrode in which the mercurous chloride is reversible with respect to the chloride ion. So the single electrode potential is E calomel is equal to E0 calomel. Okay, standard. When this concentration is 1 molar, that is called a standard value. It is 0.222, I think its value is when it is 1 molar, its value is 0.2800. Okay, E0 calomel, I will write, minus 0.0591 by N2 log concentration of Cl minus the whole square divided by the concentration of mercury, that is 1, and the concentration of mercurous chloride, that is also 1. Okay, I will write Hg divided by Hg2Cl2 solid. So this is 1. This value, activity of mercury and mercurous chloride is 1. So you can write, and this value is 0.2800 plus 0.059191. Okay, this cut. Okay, right. Log 2 log Cl minus. So now our equation now become, that is E calomel is equal to E0 calomel plus 0.0591 log Cl minus. So it's an electrode that is reversible with respect to chloride ion. So depending on the concentration of chloride ion, it develops a potential. Okay, that's the thing. Products by reactor. Okay. The next, so you know that when we take a saturated solution of KCl, this calomel electrode can be used as a secondary reference electrode. Then fourth type is known as the conventional, okay, another metal redox electrode. That is, a metal like a platinum wire is in contact with an aqueous solution of a metal of two different valency, like ferrous and ferric. Okay. So this is an example. Suppose we have a salt solution. Containing ferrous, okay, ferrous and ferric in contact with each other like this. It's an example of a redox electrode. Similarly, platinum in contact, that is an unattackable inert electrode, like platinum is dipped into an aqueous solution of a metal sword having two different valency. So when a unattackable electrode like platinum is dipped into a salt solution of a metal ion of two different valency, two salt solution of a given metal of two different valency, it constitutes a redox single electrode. Redox single electrode. And ferrous and ferric is in contact, in which a platinum electrode is dipped. Okay. Similarly, stannous and stannic. Okay, serous and serious. And the reaction involved that is SN or Fe3 plus electron reversibly give Fe2 So this is the reaction involved in this. So here the electrode is reversible with respect to the ion of two different valency. So the electrode reaction can be represented as a nuncification E is equal to E0 minus 0.0591 by N log Fe2 plus aqua divided by Fe3 plus aqua. So this is the electrode reaction, what this is. Okay. Then another typical example of this case is, in your case, that is hydroquinone and hydroquinone in the presence of HCl. Q, which platinum is introduced, platinum, got a quinone and a hydroquinone. Hydroquinone in contact with the H plus. Okay, so an example of redox single electrode. It's an example of typical redox single electrode for measuring the pH of a solution below 8. And the electrode reaction mode is an equimolar mixture of quinone and hydroquinone. Equimolar mixture of quinone and hydroquinone. This is quinone. Okay, quinone is reduced in the presence of H plus ion to hydroquinone. So typical reaction is like this. This is a hydroquinone. So it's an electrode. A quinone hydroquinone electrode is a typical oxidation reduction electrode in which the quinone hydroquinone mixture is reversible with respect to, hydroquinone is reversible with respect to H plus ion, or quinone hydroquinone mixture is reversible with respect to H plus ion. Okay, you have to remember that is so it's an electrode that is reversible with respect to H plus ion. So E quinone is equal to E0 quinone. Okay, a mixture of quinone and hydroquinone is called a mixture of quinone and hydroquinone is called equilibrium mixture is called a quinhydrone. Okay, this quinhydroquinone mixture. So E0 minus 0.0591 by 2 stand for electron log. Concentration of this hydroquinone QH2 divided by this concentration of quinone into concentration of H plus the whole square. Now on this is equimolar. Since they are equimolar, it's actually taken as 1. So when we are rearrange this equation, we have E quinone hydroquinone, E quinhydrode is equal to E0 quinhydrode, okay, plus 0.0591 by 2 log H plus the whole square. That is equal to E0 plus 0.0591 by 2 into 2 log, okay, like that, 2 to 0.0591 by 2 log H plus. So this cancel is here. So we have the equation, that is E quinhydrode is equal to E0 quinhydrode plus 0.0591 log H plus. So it's an electrode that is reversible with respect to H plus ion. So it's a typical example of various types of electrode. Now we can pass on to, okay. So I have explained this. So in connection, then we have to pass on to the reference electrode. There are two. A reference electrode, a standard electrode, is that electrode in which its potential, a single electrode potential is accurately known. Okay, an electrode, a reference electrode. So an electrode in which its potential is accurately known at a room temperature, okay, at a desired temperature. That is called a reference electrode. There are two types of reference electrode. One, primary reference electrode, and two, there are two types of reference electrode, primary reference electrode and secondary reference electrode. Okay, so a reference electrode is that electrode in which a potential is accurately known, and this electrode is used to measure the potential of any other single electrode by coupling the unknown single electrode with this reference electrode. So that is the practice usually adopt. If you wish to measure the single electrode potential of any unknown metal ion electrode, you have to couple it with a reference electrode. Then by knowing the potential of that reference electrode, we can measure the single electrode of any unknown electrode. There are two types of single electrode, reference electrode. One is primary and the second is secondary. And your only one primary reference electrode is SHE. So standard hydrogen electrode is the only primary reference electrode. It is an electrode which consists of platinum contact with the hydrogen, pure dry hydrogen gas at a 1 bar, 1 atmosphere pressure, which is in contact with the H plus solution of 1 molar or hydrochloric acid solution of 1 molar. So, and its potential is arbitrarily fixed as 0. So, E0 H plus bar H2 platinum is arbitrarily taken as 0. Okay, because the potential developed by 1 molar hydrochloric acid with the iodine gas of 1 bar pressure, 1 pressure is arbitrarily fixed as 0. So it is considered as such a standard hydrogen electrode. Any potential of an unknown electrode can be measured with respect to this, but the problem is that it is not easy to handle because it is not. That is, the problem associated is that it. I have mentioned it consists of a platinum wire attached to a platinum foil kept deep in an acid solution containing H plus ion of concentration 1 molar. And pure dry hydrogen gas at 1 atmospheric pressure 1 bar is constantly bubbled through the solution. That I have given shown the figure like this. This is the figure. Okay, this is a picture. Okay, this is a picture. You will see this. That is, a vessel is taken in which hydrochloric acid of 1 molar concentration is taken, into which an inverted glass tube is connected, to which hydrogen gas at 1 atmospheric pressure is bubbled through it. Then a platinum wire connected to a platinum foil acting as an electrical circuit contact is introduced to it. So hydrogen gas is bubbled. Then the potential develops at the inner surface is 0, simply with 0. So that is hydrogen electrode, and it is reversible with respect to H plus ion. That I already mentioned that. So the problem associated with this that it is very difficult. It is not convenient for routine work. It is not handy for routine work because it is very difficult to maintain the pure dry hydrogen gas at a 1 atmospheric pressure in a vessel. So in a routine analysis, because the practical difficulty in maintaining the pure dry hydrogen gas at 1 atmospheric pressure, it is not convenient for routine work. Second is its potential gradually changes with respect to time. Okay, for a long time. So because of this, primary reference electrode is not hydrogen gas electrode is not used as a reference electrode. Generally, that is secondary reference electrode like Kalomel electrode are used. A secondary reference electrode are those electrodes which are standardized with respect to the primary SHE. That is any reference electrode that can be standardized using SHE is called a secondary reference electrode. And example are Kalomel electrode is a secondary reference electrode, and the silver chloride electrode. Okay, this is an example of secondary reference electrode. Typical example I have explained the Kalomel electrode that I have already explained. It consists of mercury in contact with the mercurous chloride, so insoluble salt, which is in contact with the KCl solution, aqueous solution, usually saturated. A saturated solution of KCl is in which mercury chloride is insoluble salt, that is a Kalomel, to which mercury is there. So I already shown, and it has a potential of saturated solution. It has a potential of depending saturated solution 0.23 something like that. It has potential 0.2415 volt. So a saturated Kalomel electrode consists of mercury in contact with the mercurous chloride, which is in contact with the KCl saturated solution. Potential is the room temperature is 0.2415 volt. It is considered as a easily useful secondary reference electrode. And the apparatus I have mentioned. Okay. This is the apparatus framework. A glass tube with a side arm and the bent tube, low portion mercury liquid, above which there is a paste of mercurous chloride, and above which there is a saturated solution of KCl pass through this side tube. Then a glass tube containing mercury rod, to which mercury is sealed, some mercury to which is sealed, some mercury is being dipped into this bottom, acting as the electrical circuit. And side tube also contain KCl. And the electrode reaction I already mentioned is an electrode that is reversible with respect to chloride, that is chloride ion. 2 electron giving 2 Hg liquid plus 2 Cl minus. So an electrode reversible with respect to chloride ion. So it is usually used as a secondary reference electrode. So you listen to this. Okay. What is a calomel electrode? A calomel electrode is a secondary reference electrode. Depending on the concentration of KCl solution, it has a potential. Okay, 0.1 or saturated solution. It contains some mercury, liquid in contact with the mercurous chloride insoluble salt called calomel. Okay, which is also in contact with an aqueous KCl saturated solution, and its potential is usually taken as 0.024, 0.2415 volts, and is called a standard calomel electrode, so secondary reference electrode. So then we have to pass on quickly. Okay, immediately the thermodynamics of a galvanic cell. Quickly I will explain that thermodynamics. You know that when a galvanic cell works, a particular chemical reaction involving reduction takes place. A chemical reaction involving oxidation and reduction takes place in the galvanic cell, and there occurs a decrease in free energy, and the decrease in free energy of the chemical reaction is then converted into transformed into electrical energy. That's the principle. Suppose you know that electrical energy in terms of energy, that is equal to quantity of electricity into E, the EMF developed by the cell at the equilibrium. That is, you have to remember, equilibrium EMF of the cell. Suppose we know that 1 Faraday of electricity that is can cause one more. Okay, cause the passage of 1 mole of the electron. Therefore, n mole of the electron can cause n of Faraday. So the quantity of electric energy is NFE. Okay, you know that 1 Faraday corresponds to 1 mole. Therefore, for n mole, the amount of the electricity is NF into E. Therefore, the electric energy is NFE. Then, according to your energy conversion, we know that this is equal to the decrease in free energy. That is, minus delta G is equal to minus delta G. So, the decrease, the electrical energy produced is equal to the decrease in free energy occurred during the redox reaction. Therefore, minus delta G is equal to NFE. So, or delta G is equal to minus NFE. This is the first equation you have to study. So, according to thermodynamics, the decrease in free energy of a reaction is equal to NFE or delta G is equal to minus NFE. Then, according to Gibbs-Helmholtz equation, you know that delta G is equal to delta H plus T into d delta G by dt at constant pressure, that you have already studied. So you put this equation, delta is minus NFE. Minus NFE is equal to delta H plus T into d minus NFE by dt at constant pressure. Okay. So in opening this equation, that is equal to delta H plus NF into minus, okay, minus NF into NF T into d by dt at constant pressure. So this is another equation, that is minus NFE. So we have the equation like this, that is minus NFE is equal to minus NFE is equal to minus delta H. Okay. Equation. Okay, the gives Helmholtz equation is delta G is equal to delta H plus T into d delta G by dt. Therefore, minus NFE is equal to delta H plus T into this like this. So, delta H minus NFT into d by dt at constant pressure. So, put the minus, throw it by minus, then NFE is equal to minus delta H plus okay, plus NFT d by dt at constant pressure. So you can put that. So multiplying like this, okay, you can introduce like that or convenience. So according to your convenience, you can make this equation like this: minus NFE is equal to finally we have the NFE is equal to minus delta H plus NFT into d by dt at constant pressure. So that we want to get the value of delta H. Delta H is equal to minus NFE plus NFT into d by dt at constant pressure. So the value of enthalpy. So we have the second term. Delta H for the reaction is minus NFE plus NF into, so I can get represented as that is equal to NF into T d by dt at constant pressure plus minus C. So this equation for delta H. So delta G is equal to minus NFE, equation number 1. Delta G is equal to minus NFE, equation number 1. Then delta H is equal to NF into T into d by dt minus E, second equation. This is the second. Then find delta S. Okay. Now you wish to get the value for delta S. Okay, we can go to that. That is delta S is equal to symbol. You can remember comparing this equation. Delta G is equal to delta H plus T into delta G by dt at constant pressure. Okay. T delta S and we have the equation. Delta G minus delta H is equal to T into minus N T into D minus NFE by dt at constant pressure. Okay. Minus NFE by dt at a constant pressure like this. That is equal to minus for this equation. This minus differential of minus and minus T NFE NFT into. So we have the equation NFT into delta H my delta G minus delta G is minus NFT minus NFT into dE by dt at constant pressure. Okay, this equation like this. And if you already know that the conventional form delta G minus delta H is equal to minus T delta S. This conventional form you already. Delta G is delta H minus T delta S. So you understand this. Comparing this one, these two. Compare these two. You have the equation this and 2. Minus T delta S is equal to minus NFT d by dt at constant pressure. So we are right. Delta S is equal to NF T get cancelled. So negative also cancel. NF into d by dt at constant pressure. Okay. So delta S is equal to NF into d by dt at constant pressure. So we have the three relation. So thermodynamics, we says that delta G is equal to minus NF E, and delta H is equal to NF into T d by dt at constant pressure minus E. This equation number 2. And finally, delta S is equal to NF into d by dt at constant pressure. These are the three relations that we have to study in connection with the thermodynamics. Okay, so please remember: 1. Delta G is minus NFE. 2. Delta H is equal to NF into T d by dt at constant pressure minus E. Okay. Then 3. Delta S is NF into d by dt at constant pressure. If they are on the standard state, delta G is equal to NF E0, delta S is equal to NF into T d0 by dt at constant pressure minus E0, and delta S is equal to NF into d0 by dt constant pressure. So next class we have to pass on to the relation between the equilibrium constant and delta G of a reversible reaction. Okay. So time being, I am winding up now. Thank you for listening me. Okay. Thank you very much.